Hello, I'm Nicholas, and this is my video presentation of Lab 3 on magnetic field of a bark magnet. The introduction. The purpose of this lab will be to measure the distance of a magnetic field due to a small bar magnet. Then compare our measurements to the distance dependence predicted by the equations for the on-axis and off-axis magnetic fields. In a brief look into the results, the magnetic dipole moment that I calculated was 5.941. And then we also found n, which is negative 2.3567. And then our simulated off-axis magnetic field was 2.7 to the negative 5 teslas. And our experimental axis magnetic field was 3.87 to the negative 5 teslas. And some fundamental physics concepts. The Bivat-Sarvat law is the main formula that we'll be using for this lab, which is located right to the right. And then the distance dependence formula of a bark magnet is also located to the right of this. And some assumptions, we will assume that the bark magnet that we'll be using today will be acting as a magnetic dipole. The lab procedure, the bark magnet was the system, and everything else inside the lab room is considered to be the surroundings. Initial conditions, bark magnet and the Tesla meter, the app on the phone. To set up for the lab, we first needed to find where on the phone where the strongest magnetic field was. We accomplished this by moving the phone vertically to find the maximum absolute value of x, then move the phone horizontally to find the maximum value of y. Lastly, we marked those spots with 2 pieces of tape. The data collected after completing the experiment using the bark magnet and ruler, we found that the on-axis distance for the magnet to the smartphone. We plugged the measurements into the Excel sheet for it to be linearized into a graph, and this is what we have located under that. And these are also the results collected and calculated for the off-axis magnetic field of the bark magnet. And some observations. When the magnet meter is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The position of the magnetometer has an effect on the measured x component of the magnetic field. And the code and my hand calculation for the magnetic dipole moment is located right here. This is how I got 5.941, and then I plugged that number into my code. And this is the setup for the observation points for the on-axis and off-axis model, according to the origin, which is the magnet. And then this is the setup for the 45-degree angle example. And here's my model. So the orange arrows show the on-axis magnetic fields. The cyan are the off-axis. Purple is the 45-degree off-axis. And the calculations for the 45-degree vectors are shown below. Some results. The theoretical off-axis was 2.7 to the negative 5 teslas. The experimental off-axis field was 3.87 to the negative 5 teslas. There was a 36% difference. Discussion. Possible source of error. Other magnetic fields such as smartphones and laptops could have affected the magnetic fields at that time. And incorrect phone placements / distance measurements. So some measurements could be a couple centimeters off, and recording measurements from the app. So the net magnetic field of Orlando in the lab was to be said to be 49, but mine phone showed like 39, so that was a little bit off there. And then the what if questions. So what if you haven't orientated your experiment to compensate for the magnetic north? and had instead laid out your measurement stick at some intimate angle with respect to the Earth's magnetic field, how your results have changed. Our values for the B of the bar magnet would not be correct and would skew towards the Earth's magnetic north. This would make it harder to take into account our calculations. What if you were to stick two identical magnets toward end to end and run the experiment again? How would you expect the measurements to differ? The magnetic fields would still open and point in the same directions, but would double in magnitude. And this concludes my video presentation for Lab 3.